All right, hi, my name is Dave Filecipher. I'm a PhD candidate in computer science at the University of Southern California. And this project is actually a collaboration between three different labs. The interaction lab led by Professor Maya Matarik, the robotics embedded systems lab led by Professor Gaurav Sukhatme, and the computational learning and motor control lab led by Professor Stefan Schall. And I'm going to talk to you a little bit about the interaction lab. We are a lab that's mostly focused on socially assistive robotics, although we do other things. That is the goal of the PR2 project. And we're doing this in a number of different domains. We're working in motor task rehabilitation for post-stroke patients post-stroke. We're working with elders and patients with Alzheimer's on exercise therapy. And we're also working with children with autism, trying to study how children play with robots. And one of the things that we're working on is fundamental behaviors for human-robot interaction, and especially ones that serve therapeutic treatment or diagnostic approaches. So one example is coverbal behavior generation, which we are using currently in our post-stroke project to generate responsive behavior in addition to simple verbal commands. Another example of research we're working on right now is using an overhead camera for interaction. Actually, one of the benefits of the PR2 project is going to allow us a robot with a lot more sensing than our robots currently have. And that onboard sensing will hopefully allow us to do people detection in real time. And talk more about that, I'm going to hand this over to another PhD student in the interaction lab, Ross Mead.
Thanks, Dave. So my name is Ross Mead. I'm a third-year PhD student in the Interaction Lab. And as Dave was mentioning, one of the things that we're working on is human activity recognition. So you can actually see right here, this is something that we integrated yesterday. This is actually a people finding package that's available already provided by Willow Garage. The link is there. I don't know if everyone can see it, but it's doing head tracking and leg tracking, and the end goal would be to combine this all together and do full person tracking in an environment. This is kind of a hallmark of the whole ROS community, is that everyone's contributing, everyone can share this code. Again, we just integrated this just yesterday, having never used it before. We can integrate this with Dave's overhead tracking system to get a more interesting estimate of what a person's doing. So where we would want to take this actually is getting into human attention. So we would want to see where a person's looking and what a person is attending to in an environment. And just as an example of why we want to do that, we really focus on having robots to interact in a social scenario. And in order to get into that social scenario, well, you have to position yourself in such a way to communicate to the person that you want to be in the scenario. So we would want to take these attention spaces that we can get from our person tracking system and place the robot appropriately so that it's communicating that it does want to interact. So for example, you can see on your left here a dyadic scenario where you have a person and a robot facing the person, and then you have a shared joint attention space. Or you have this triadic interaction scenario in the center where you have two humans, a robot, and they share, again, another space. And then you can get into these larger group scenarios to your right. Now, it can seem actually rather simple if you just look at the way things are right now. People seem evenly spaced around a circle. But it's not so much that people just have this inherent desire to get into circles. It's actually a product of the attention space and trying to perceive certain things that are going on in the environment, such as someone speaking. And to kind of show where we'd want to extend this kind of stuff, you'd want to take this into a scenario where you're collaborating. So you have a shared attention space, but you're trying to focus on collaborating, working with an object, or working with tools, maybe playing a game of some sort. You know, people do this putting a puzzle together or playing chess, those kinds of things. Just having this shared object that you can interact with and talk about. Also, you have a scenario here where you're presenting something. So actually, as you can see, I change my body orientation and even use a deictic gesture, a point, to refer to something on the screen. We want a robot to be able to both respond to this kind of scenario and produce the scenario itself. So when interacting with a person, be able to shift its body orientation and use deictic gesture to communicate something about an object. This is particularly important when in the context of therapy with children with autism, as their deficit does not allow them to pick up on a lot of these social cues. They respond slightly differently to a robot, and that's a continued area of investigation in our lab. Also, something that we're really interested in is the idea of moving. So we go from a face-to-face scenario to suddenly a side-by-side scenario. Suddenly the distance that we maintain between each other becomes closer, yet we still share an attention space directly in front of us as we move. Even extending this, we would go into using attention and using that to communicate intention or recognize intention. So this is actually just a really quick demo that we threw together yesterday. Just the robot's going to be driving around, and as it's driving around, it's actually looking ahead to where it's going. It's also trying to, right now it's not looking at objects that are around it, but in the future we're going to look at salient objects in the environment as well as people. So the robot's doing this little look ahead, and it's communicating to you not where it's at now, but where it's going to be. So a lot of people, either will walk directly at the robot, they could care less, they know that the robot's going to go around them. Traditionally, what's nice about this is that the robot is telling you where it's going to go, so hopefully people will respond in a more appropriate social way. So one thing that you kind of see with all this is you've got this robot that seems like it's doing, hopefully some sort of intelligent behavior. But for a robot to do something intelligent, it has to be aware of its own physical embodiment. And so to talk a little bit more about how we're going to have the robot sense its own environment, embodiment, and information about its sensors, I'm going to hand this over to John Kelly.